Alright, so in this video I'd like to go a little bit more in depth and analyze the connections between my new binary cube puzzles because these are actually quite related to each other, and it also has to do with something called holding points and layer independency, so it is quite interesting. Now, in order to understand these concepts, it does help to know the different ways that one can view moves that you can make on a puzzle and how layers can be defined and the differences between, shallow turning and deep turning, deeper than origin turning. So in order to explain these concepts a little bit before jumping straight into the deep end, we'll take a look at a standard 3x3 cube to begin with. So on a 3x3 cube, we have 3 different layers per each axis of rotation, and the standard way we define moves on a 3x3 is by turning the outer layers like this, so that would be an R prime, an F, U move, and so on and so forth. And so those are the outer layer turns that we make, and that's the standard of how we, denote moves on a 3x3. But there are also other ways that we can view moves on a 3x3 cube. For example, instead of just turning a single layer like this, we can instead choose to turn 2 layers at the same time like this, and we sort of call that a wide move classically, but this can also be viewed as a double layer move, or it can even be viewed as a deeper than origin move. And the reason is that if you consider an origin move, that would be going straight through the origin point of the puzzle. But as you can see, these 2 layers encompass more than half of the puzzle. They go past the origin point, and so we can think of this as being a deeper than origin turn, this double layer type of turn here. In comparison, the outer single layer turns like this would be shallower than origin because they don't go up to the origin, they stop before it. Now, if we think about the standard view of moves on the 3x3 cube, where you do all of these outer layer turns here, we can think of the core in the puzzle, that is the spider in the middle that holds the thing together, as never moving, right? So we can sort of think of that piece as being fixed in space and never moving around, unless of course you rotate the whole puzzle, but in this case puzzle rotations aren't really important to think about when you're defining actual moves. So the core is always going to stay fixed in space whenever you do any shallow layer turns like this. And so we call the core of the 3x3 a holding point in that sense, because it is held fixed in place where everything else will turn around that fixed piece. And I know that you can't really see the core on a 3x3, but you definitely know that it's there. Now the thing is that choice of the core being the holding point of the puzzle is actually pretty arbitrary. You can actually choose any piece in the puzzle to actually act as the holding point. And what might that look like? How might that change things? So let's see what would happen. So instead of choosing the core as the holding point of the puzzle, let's instead choose a different piece on the outer part of the puzzle. Like let's say we pick a corner piece. Let's pick this orange, green, yellow corner piece. We're going to define this to be our new holding point. So what that means is that this piece is always going to be fixed in space. It's never going to move around with any of the moves that we make on the puzzle. So how's that going to change what the moves look like? Well, let's think about what moves that we can make that keep that corner piece fixed in place. Well, we can do a turn on the U layer, that's totally fine. We can do an R layer turn, that's also fine, and an F layer turn. None of those 3 moves affect that piece and it stays fixed. But you can see that we can no longer do a D move, right? Because that's going to move that piece, and we said that this was going to be a holding point, that it was going to be fixed in place. So we wouldn't be able to do a D move or an L move or a B move anymore. But we still want to be able to do all of the moves on the puzzle that we had access to before, right? So how do we get around this? Well, what we can do is instead of doing the single layer turns, we can actually start to incorporate those double layer moves. For example, if we want to do an L move, what we can do instead is a double layer R move. Now, if you look at this, you can actually see that this was actually equivalent to doing a single L move on the puzzle. See that? It's equivalent to doing an L move. However, by the way that we did this move with the double layer deeper than origin turn, the holding point stayed a holding point. It actually did stay fixed in place, and it didn't rotate or move around the puzzle. And so this is how we can get around that. We can use double layer turns to incorporate any holding point that we wish. And if we want to do a D layer move, well, we just do a double layer U move, or a deeper than origin U move. And finally, B is just going to be this double layer F move. And you can see that doing any of these moves, it's always going to keep this corner piece fixed in place, and therefore it acts as the holding point. So we can see that work right there. Now, it doesn't just have to be a corner piece. We could also, for example, choose an edge piece to be the holding point. Let's say we choose this orange-green edge to be our new holding point. Then it works in a similar sort of way. We can define our moves based around that holding point. So our U move would stay the same, and our D move would stay the same because those don't move that edge. Also, F is the same, and R is the same. But in order to do an L move, we'd have to do a wide R move, and that keeps the holding point. And then to do a B move, we'd have to do a wide F move. So you can see that we can just redefine our moves, and that also is going to redefine our holding point for us. And to finish this off, if we wanted to pick a centerpiece as the holding point, that works too. Our F, L, and B would remain exactly the same. Our D move would also stay the same. As you can see, that's not moving that center. But we would no longer be able to do a U move, right? Because that would rotate the center around. So to get around that, we do a wide D move. And so you can really see here that that centerpiece is now acting as our holding point. So that's the idea behind holding points on a puzzle. But what else is this telling us? Well, it's kind of illustrating that a puzzle doesn't really have as many free layers that are independent of each other as you might think. So a 3x3 cube, while having 3 layers per axis of rotation, it really only has 2 independent layers of axis per rotation. And to illustrate why this is the case, you can think about the fact that any single move on any one of these 3 layers can actually be defined as a move on the other 2 layers, and then a global rotation of the entire puzzle in space like that. So you just saw that there. We see that doing an L move is actually equivalent to doing an R move and then this middle slice M prime move like this, and then rotating the whole puzzle like that. That's equivalent to doing an L move, but you can see that we didn't actually do a move on the L layer, right? It really stayed put, and we only moved the layers around relative to it. And this can be said for any of the 3 layers on any axis. Say that we want to do a middle layer slice move like this. Well, an M prime move would actually be equivalent to doing R prime, and then L, and then rotating the puzzle like this. So you can see that we actually just need 2 layers on the puzzle to actually define all of our moves, because we can sort of rotate the whole puzzle in space to kind of change the perspective of looking at it as a different layer moving. So that's the interesting part here, is that in reality, a puzzle with n layers per axis only has n-1 independent layers per axis. So we can define all of our moves around that, and that's also kind of related to the idea of holding points. Like I said, if we choose a different piece to be a holding point, then we're sort of defining our moves around that point. Alright, so what does all of that have to do with the 2 binary cubes, right? Well, you know, these puzzles are kind of similar to a 3x3 cube, so you can kind of imagine that the analysis might be a little bit similar, but really these concepts should be thought of very generally. And that's the important thing here. But to sort of analyze these puzzles a little bit closer, let's kind of think about, you know, how many independent layers per axis do we have on these puzzles, and what kind of turns do we make? Well, let's start with the binary deep cube, because I think this one's a little bit easier to understand. So if we kind of consider the binary deep cube from the standard point of view, this corner piece is a special corner piece, and any move that we make must move this corner piece, right? You can only make turns on layers that contain that corner piece, and the other layers are going to be blocked and cannot turn. And also we have, of course, that locked out axis of rotation that doesn't allow any moves at any point in time. And so if you kind of think about it that way, this puzzle actually is only going to have one independent layer per axis of rotation, because if you look at any axis where you have a layer that can turn, that is the only layer that can turn. The other one is going to be blocked. And so you only have one independent layer per axis of rotation on this puzzle. And the same is also going to be true on the binary fused cube as well, because, I mean, it's kind of obvious you have this fused corner block here, so there's only one free layer to turn for any given axis of rotation. Now back to the binary deep cube. If we sort of think about this a little bit more, the binary deep cube and the binary fused cube actually do have one piece that's sort of in common with each other, right? They kind of have a special corner piece. On the binary deep cube, it's just this little corner piece here. But on the binary fused cube, it's this bandaged corner block, right? This is kind of like a special corner piece that's different from all the rest. So we can sort of think about the binary deep cube in the perspective of having a special corner piece. So let's do a little experiment here. Let's take the binary deep cube, and instead of considering the core as our holding point, kind of like we would naturally do for a 3x3 cube, let's choose our special corner piece to be the holding point. And then let's see how our moves have to be defined around that. So I'll hold the puzzle so that the special corner is in the bottom back left position in space, like this. And so this is how we're looking at the puzzle now. So, as before, this is going to be our holding point, so all of our other moves that we have must keep this piece fixed in space. So let's say we want to do an R turn. Well, we can't do a shallow layer R turn, and that's because of the special mechanism here. But we can't do an L turn because that's going to move the piece that we set as a holding point. So in order to get around that, we can do a deeper than origin move here. We can do a double layer R move, right? And that's equivalent to an L move there. So we can do that just fine. Okay. And can we do a D move? No, we can't, because that's going to move the holding point. So instead, we can do a wide U move like this, and then that defines that turn. And can we do a B move? Nope, because that would move the holding point, so instead we'll do a wide F move. So those are the kinds of moves we have available. We can only do wide or double layer or deeper than origin, whatever word you like, moves for these front three axes here. You can never do single layer turns under this definition of having this piece being a holding point. So you can do wide R moves, wide U moves, wide F moves, and so forth, as long as they're available to move, right? Because remember, we still have that locked out axis that cannot turn at all. So if you just stare at this for just a moment, it might be pretty obvious to see that in fact the binary deep cube, when looked at from this perspective, is actually behaving very similarly to another puzzle. What is that other puzzle? Well, I think you might have guessed it. It's actually the binary fused cube. If you think about the way we normally look at the binary fused cube, you have these three layers that can turn up, right, and front. Kind of like what's now happening with the binary deep cube, we can make moves on those axes. And whenever we make a move, the X piece that's inside on the binary fused cube is going to move around. But if you look at what's going on this binary deep cube right now, whenever we make a move, that X piece is moving around the puzzle, and it's actually moving in exactly the same way that it's happening on the binary fused cube. Whenever we do a quarter turn on any of these layers, it's going to flip which of the other axes has the X and is locked out, and which one is not. So you can see here it's actually working in the exact same way, and the moves that we're making on this puzzle can now be made analogously on this puzzle. So you can see that from this perspective, these two puzzles are almost equivalent to each other. But of course, they're still a little bit different, right? And what is that difference? Well, here we're making deeper than origin turns on the binary deep cube, but on the binary fused cube, we were making shallower than origin turns, as you can see. So that is the difference between the two puzzles. From this sort of perspective of having a corner piece as the holding point, the binary fuse cube is a shallow turning puzzle, but the binary deep cube is a deeper than origin turning puzzle. And we can see that right here. Pretty interesting. So that's looking at this puzzle from the perspective of having this corner piece, the special corner piece, being the holding point, instead of the locked out axes being the holding point. Right? But if we think about that a little bit, that sort of suggests something, that maybe what we can do is actually consider the binary deep cube's holding point, which is the core, or I guess the locked out axes, which are also connected to it. And maybe on this binary fused cube here, we can choose that piece to be our holding point instead of the bandaged corner block. What would happen then? Well, let's find out. So here is our X piece, and we're now going to say that this X piece is our holding point, right? So this is our piece that's going to be fixed in space, and all other moves that we define must keep that fixed. And I'm going to hold the puzzle from this perspective now, and it might take you a second, but it might be kind of obvious why we're going to do this, because we can see that this is kind of like our special corner piece, and then our special corner piece is also over here on the binary deep cube. So we're going to hold the puzzle like this, and now let's see what moves that we can make. Well, we can't do, regular R, F, or U moves here because, of course, we have the bandaging. Can we do an L move? Well, theoretically, yes, but remember, what we're trying to do here is keep the axis or core piece here fixed in place. This is now our new holding point. So we can't actually do an L turn because that's going to move it to another center. So instead, what we have to do to get around this is, as before, do a deeper than origin turn, and this time on R. So we can do an R wide move, or a deeper than origin R move, or a double layer R move like this. This is acceptable. You can see that from this perspective, the X piece is going to be fixed in space, and it's going to act like the holding point like we want. So this is good. So we can do, let's see, an R prime move, and can we do a B move from here? No, because that's going to move the X piece. And if that's our holding point, we don't want it to move. So instead we can do, let's say, a wide F move. And that works just fine. Perfect. So we have that. Now can we do an R move? We could, but remember, this is our holding point. So instead we'll do a wide L move, like that. Okay, that's fine. We can even do another one like that. And from this perspective, we could maybe do an F move, but remember, nope, that doesn't work. We want our holding point to be a holding point, so instead we can do a wide B move, let's say. Right? So now if you think about it, looking at the puzzle from this perspective, and looking at the moves that we're making on the binary fuse cube from this perspective, you might notice something, and that is, if I can remember what I did here. Here we go. You might notice that this puzzle is now behaving very similarly to the classic view of the binary deep cube, right? You have this bandaged corner, and you can see that we have to make moves that involve this corner piece with these deeper than origin turns. And the reason is because of the bandaging, right? That's kind of superficially obvious here, but really that's what's going on. And now our top and bottom axes are fixed in place. So it's always the top layer and the bottom layer that can never turn at all. And that's just like with this binary deep cube over here. The top and bottom layer are never going to turn. And the types of moves that we can make are only going to be R, B, L, and mechanism work for me, F moves. So those are the same moves that we're able to make on the binary deep cube from its standard perspective of viewing it. So that's really interesting. This puzzle is virtually behaving exactly the same. Again, not quite the same, right? Because clearly these puzzles have different pieces. But the difference is that when we're looking at the binary fuse cube from this binary deep cube perspective, all the moves that we're making are deeper than origin moves on this puzzle, but on the binary deep cube, all of those equivalent moves are going to be shallower than origin moves. So that's the difference between the two puzzles. From the binary deep cube perspective of viewing the puzzles, the binary deep cube is a shallow turning puzzle, and the binary fuse cube is now a deeper than origin turning puzzle. So the really interesting part here is you can see that this is now flip-flopped from what we had before, right? From before, when we were looking at both of the puzzles from the fused cube's perspective, then the binary fuse cube was a shallow turning puzzle, whilst the binary deep cube was a deeper than origin turning puzzle. However, now when we're looking at both puzzles from the perspective of the deep cube, the binary fused cube is now a deeper than origin turning puzzle, which is the opposite. And then the binary deep cube is a shallow turning puzzle, which is the opposite of what we just saw before. So that's really the connection between these two puzzles. These two puzzles are, in fact, one and the same. The difference is one is going to be shallower than origin turning, and the other is going to be deeper than origin turning, regardless of which perspective you take. So, in essence, the binary deep cube's perspective is take fixed axes of rotation and have a constantly moving corner piece. And then, in that perspective, the binary deep cube is shallow turning, whilst the binary fused cube is deeper than origin turning. And on the flip side, with the binary fused cube's perspective, we have constantly moving axes, as you can see, and a fixed corner piece. And from this perspective, the binary fused cube is a shallow turning puzzle, whilst the binary deep cube is a deeper than origin turning puzzle. And to go from one perspective to the other is simply changing what your holding point is. So the binary fuse cube's perspective is to have the corner piece be the holding point, while the binary deep cube's perspective is to have the locked out axes, or rather the core of the puzzle, I guess, be the holding point. So I hope that explains a little bit of the theory and connection between the two binary cubes. One puzzle can be viewed as the other puzzle by simply switching your perspective on the holding point, and it works for both puzzles in both ways, and it changes which one is shallow turning and which one is deeper than origin turning. So I hope you found this interesting, and thanks for watching.